Hey everyone, excuse me. Welcome to a little video clip with regards to structures of solids and unit cubes. This topic is in our textbook, although in my opinion it could be a little bit more thorough if you really wanted to get into the nitty gritty nuts and bolts of these cubes. I want to look at three basic kinds of cubes. And I think if you've been in class, we've already studied them a little bit. The first one, the simplest one, is just where an atom occurs in what's called the unit cell, the simplest repeating unit, having one atom at every corner. Here's the cutaway version. It turns out that every atom at the corner contributes 1/8 of its volume to this particular cube, 1/8 to the right, another cube on the right, 1/8 to another cube in the front, etc. Another one called the body-centered cubic. I have them down here. You can print off this PDF sometime if you'd like. Not a bad idea to look at. As one atom entirely in the center of the cube, and then same story, 8 others on the corners. And lastly, the third but slightly more complicated version is where I have one of 8 identical atoms, well, maybe not identical, probably identical, on the corners. And another atom could be the same or different on the face. But this atom on the face contributes 1/2 of its volume to the unit cube, and the other half to, say, the front, a cube in the front, to the left, in the back, or to the right, or to the below, or to the above. So, geometry is pretty cool, but it can get kind of involved. One question we like to ask is the size of the unit cube. In the language of our text, often it'll call the length of the cube A. If it's simple cubic and the atoms like to pack together as closely as possible, they're touching each other, so 2 radii added together add up to the side of the length of the side. In a slightly more complicated version, a face-centered cubic, I might imagine that this atom in the face and this atom on the face, or the atom on the top face or bottom face or left face or back face, contributes 1/2 of its volume, 2 radii, and the diagonal of the face would be radius, 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 or 4 radii, and a squared plus b squared equals c squared is what Pythagoras said. So a squared plus a squared equals this long diagonal squared, and I got a funky formula that looks like this, relating the radius of the atom if this atom is the same as this atom. If they're not the same atoms, then they could be different volumes or different sizes, right? With the body-centered cubic, even a little bit more complicated than that, but assuming they still touch each other with 1 atom in the center and 4 atoms on every corner, the atoms are larger than just this. This is the ball and stick model, so if you fill in the size of the atom, maybe this is this atom, and this radius is this atom. The diagonal down the center of the box is 4r. This is A, called A, whatever the A is. But this diagonal on the face would be this one squared plus this one squared. That's a squared plus a squared, take the square root. So that diagonal is a squared plus b squared equals c squared. You can sit down with this and prove it to yourself. It's all, I don't think I made any mistakes here, but it's not obvious at all. So therefore, on this right triangle they have highlighted in red here, this is one length of the leg at a right angle to another leg, which is opposite the hypotenuse. These are some tools that we might use to analyze the size of the atom, the mass of even the mass of an atom, or the mass of a unit cell. That's a summary of what we just saw. So if I relate those together, I said a squared plus b squared equals c squared. I took the square to both sides. And this is an odd relationship for that body-centered cubic. A is usually the length of an edge, and the volume would be then length times width times height, and since they're all the same in the cube. A slightly more complicated version would be, what if the atoms aren't all the same size? Well, that gets kind of messy, but that's interesting to think about. Here I've summarized those results. You could either remember these or remember these, or you could derive them if you were really motivated. But some of the problems I'm about to work involve either this relationship or this relationship. So for the simple cubic, either of these, body-centered cubic, face center cubic. Salt's a really weird one. That's normal table salt. It's kind of weird because the atoms are different sizes. So I have chlorines on the, and I could switch it out. I could put the sodiums on the corners, but everything else would be, it would be actually similar. I mean, equivalent. Try it yourself. I have 8 chlorines on the corners, and so 1/8 and 1/8 and 1/8, 1/8 and 1/8, 1/8, 1/8, 1/8 add up to 1 chlorine atom dedicated to this cube due to the chlorines on the corners. Chlorines on the faces have 1/2 and 1/2 and 1/2 of their volume dedicated to this cube. The other half is dedicated to the right or the left or the bottom or the top. And therefore, what it comes down to is four chlorine atoms dedicated to this cube. There's one sodium all center, full on to this cube. But then the other sodiums on this one and this one and this edge and this edge. Think about it, the atom on the edge, say this atom or this atom or this atom or this atom, donates 1/4 of its volume to the cube. And so 1 in the center plus 1/4 of 12 sodium atoms on the edges. Hang on, I gotta pause this for a second. I apologize. Sorry about that. I'm back. No, I thought I screwed it up, but I'm looking good. And so it's oddly enough N4Cl4, which boils down to NaCl because it's a +1 -1 ion, but the unit cube itself really does have 4 sodium atoms and 4 chlorine atoms. Body center cubic. Let's look at one of those again. Cesium chloride. The cesium fits in the center of the cube, so that dedicates all of its volume to the cube, the unit cell. But again, the corners are 1/8, and so it's 1 chlorine altogether from the corners and 1 cesium. Here's another weird one. Let's see. On this one, I have 2 oxygens in the center and 1 titanium on the center. I have 1 titanium on each of 8 corners and 4 oxygens on the faces. So 4 oxygens on the faces, half of this oxygen, half of this oxygen, half of this one to that particular cell. And it comes out something like this. 2 titaniums. 1 titanium on the interior totally dedicated to that cell, and then titaniums on the corners as well. This may take some practice. You may have to go back and look at these some more. Here's a weird one with arsenic totally on the interior, 2 arsenics on the interior. Nickel, 8 nickels on the corners. That's 1/8 times 8 for the nickels. And yeah, so what does that all add up to? That's 1 nickel here and 4 more nickels on the edges, total of 2 nickels and 2 arsenics totally inside. But that boils down to like an empirical formula of nickel arsenide, nickel arsenic. I'm getting a little bit tired of this already. I don't know about you. But I have more examples here if you feel the need to look at them or try them. These actually come from our textbook, so I can't claim that I authored them. Here's a fun one. It's all kind of crazy. With thallium, barium, oxygen, copper, and calcium. And if you really felt motivated, you'd print this PDF or load the PDF and practice on this one over here. I have no idea what that particular material is used for. But anyways, let's go on to a different set of calculations. Here's magnesium oxide. They say it looks very similar to sodium chloride. They give me the density of magnesium oxide. Oh, no, actually they don't tell me that it looks like sodium chloride. I deduced that it looks like sodium chloride instead of zinc selenide. Zinc selenide looks like that. But doesn't this one look very similar to this one? I think so. So if that's true, I did a little calculation. I said 4 magnesiums and 4 oxygens in one little cell will come out to similar to as if I were adding up the molar mass, 161.24 AMU per cell. Then I did a funky calculation, a really weird conversion, but it's not done very often, but it's a good fundamental thing to keep in mind. 6.02 10 to the third Avogadro's number of AMUs is equal to 1 gram. So in a way, this changes my AMUs per cell into atomic mass units per cell into grams per cell. Of course, that's a small number of grams in one little cell, but that cell right there we're looking at has this mass. The volume would be, therefore, then since I know the density, I take that grams per cell and change it into a cubic centimeter per cell, because they told me the 3.58 grams per milliliter. Interesting. The grams cancel, leave me with cubic centimeters per cell, or just cubic centimeters for the volume of a cell. And if that's true, then I go ahead and take the cube root of that to find the area, not the area, the length of one cell, the length of one side of one cell, 420 picometers. Now, interestingly, if you look back, the question does ask you about the sizes of the ions, but I consulted an expert, my colleague up here at the U, and he agrees there's no way to tell without additional information how those radii distribute themselves, or what the size of the oxygen versus the size of the magnesium could be. But at least I do know the size of the cell. Excuse me, I'll be right back once again. All right, another question. Here they give me the size of the unit cell, the A, from one nucleus to the other nucleus, and I'm supposed to find calculate the length of the edge. Calculate the length of the edge of the cell. Oh, and the density. Oh yeah. So, what's this? Oh, from center to center. So from this potassium to this chlorine, or vice versa. I don't know which. So from here to here, it must be twice that amount, and that's the size of a cell. Yeah. And let me take that and find the volume of that. So the cube of A would be the volume, and change it to centimeters, meters to centimeters. Take the cube, find the volume in milliliters. And we noticed it was just like the sodium chloride, so it had 4 potassiums and 4 chlorines in every unit. I went ahead and added up 4 potassiums and 4 chlorines to get the AMU per cell. Then, just like I did before, I took the AMU to gram equivalents and changed the AMUs to grams. Of course, it's a small number of grams for that one cell. And then, this is the cute thing. I took the 4.96 10 negative 22 grams per cell and combined it with the volume for the cell, and the cells canceled in a sense, and I end up with grams per volume, and that's known as density. So potassium chloride has a density of about 2 grams per milliliter. Interesting. Here's another one. It's a tricky one. Cesium chloride. We saw the unit. It was a body-centered cubic. But in any case, I'll take the AMU per cell. Again, change it to grams per cell with this cute little Avogadro's number gram conversion. And then I use the density, 3.97 gram per cubic centimeter they gave to me right here. So I found the volume of the cell. The volume is the edge cubed. So there's my cesium, there's my chlorine. I called this the radius of chlorine. This is the radius of, I'm sorry, I screwed that up, didn't I? No, that's right. Radius of cesium, radius of cesium, radius of chlorine. Oh, 2 radii of chlorine. Chlorine's in the middle of this cube, I'm imagining. And the volume would be that. The edge would be the cube root of the volume. The diagonal of the face, so say from here to here, would be that number, a squared plus a squared, take the square root. And the diagonal of the cube, which is, we've already gone over this, believe it or not, above, but it's harder to see, would be the length of one side squared plus the length of the diagonal squared to give me the length of the cube diagonal. Change it to meters. Another word for that is 715 picometers. Then they wanted me to compare that, 715 picometers. Oh, actually they wanted me to, so from here to here, through the center of the cube is 715 picometers. So the distance from the center of the cube, the center of the chlorine, to the center of the cesium would be half that number. And then they wanted us to compare that to some measurements they had found somewhere else. Comes out pretty close. Geometry, geometry, geometry. Always with the geometry. Here's just another way of saying the cesium chloride, body-centered cubic. Do I have time for one more? I don't know if I have motivation for one more. Let me see. Where am I at? Let me choose which one I want to go over with you. Alright, I've chosen one more, although I have a couple of others on this PDF you're welcome to look at and see. My video is probably already long enough or too long to go on YouTube, but we'll find out. If I can't link it to YouTube, I'll just put it on the Canvas page. So, closest pack, cubic closest pack, another name for the face-centered cubic cell. I have 4 atoms per cell. I'm assuming, oh, they tell me it's nickel, face-centered, okay, and they give me the density of nickel as well. This is a formula form we found earlier for the face-centered cubic, that the radius of the atom would be square root of 2 over 4 times A, and the A being the length from one edge of the cube to the other edge of the cube. Solve it for A in relation to R. So if I cube that A, I get this odd relationship. And so what? I don't know. Then I took four atoms per cell, changed them to nickel atoms per mole, and then from mole to grams, or in other words, a mole of nickel would weigh 58.67 grams from the periodic table. Then I also, let's see, what would this do? This would cancel my atoms. And then I took the density they gave me, 6.84 grams per milliliter per cubic centimeter. The grams cancel. So this math gives me the teeny tiny volume for one of those nickel unit cells. So yeah, if I know the volume is equal to 32 over square root of 2 r cubed, and this is the volume, then I just take the volume equals that formula, solve for r, and you find the radius of a nickel atom. Whoa. Pretty weird. Here's another one. Why not one more, eh? Another face-centered cubic. The edge length is 392 picometers, and the density is 21.48. Man, that's a dense metal. Metallic solid. A squared plus A squared equals, and they touch here, so that's 4 radii. And so A equals square root of 8 radii. And the edge length from here to here would be then, so I'm curious about what A is. No, they told me what A is. A is 392 picometers. I'm curious what R is. Calculate the atomic radius of an atom of nickel. There you go. So if I knew this one, I could solve for this one. I knew this one, I solved for R. Pretty simple. The volume of the cell, something like this. The volume is A cubed. And so I just cubed that picometer number. Or you know what, actually I changed it to meters first. And then, oh geez, well I could have changed this meters to centimeters right away. Then when I would have cubed it, I would have gotten cubic centimeters. But if you forget to do that, you can do that later, right? Change meters to cubic centimeters. We did this way back in chapter 1, and even the review chapter. So the mass of the cell would then be, here's my volume, times by the density. The cubic centimeters cancel. There's my mass of the cell. But since there are 4 atoms in a cell, it would be even a smaller mass than that. Then if I say that this many atoms are in 1 mole, I can get the grams per mole. And then I look that up on the periodic table, and it looks like it's platinum as a metal. Whoa, that's not nearly enough time to assimilate all this junk, and there's even more up here I didn't go over. So if you guys feel like it, study these PDFs. I know there'll be a question or two related to some of this junk. Maybe one difficult calculation, maybe one more simple one where we look at the number of atoms in a cube. Not even this hard. Probably something more like this, or something like this. It could be one of those. Thanks for watching, guys. Good luck studying, and we'll see you in lecture. Yay.